Okay, thank you. So I will present some topics more about the details of deep learning. So I will just start by a short introduction, another time, a short introduction to machine learning. Then I will go much into the details of deep learning basics. Then convolutional neural networks. I will speak about transfer learning, semantic segmentation, and then I will conclude. Okay, my first part of my introduction is largely due to this book, so I just want to cite it. And then also some slides are from my colleague Damien Muselet. So I thank him also for this. So as we already talked about, we are considering some machine learning tasks. And in this part, I will mainly consider two different tasks. The classification task, where we want to predict some probabilities, or the regression task, where we want to predict some values given some input. Okay, and here I will consider the first step where we have the feature extraction, and then the machine learning step where we have the classification and regression, and then after for deep learning, as Carol said, this part of feature extraction will be included also in the machine learning part. But let's consider a simple task like, for example, crowd counting. In this task, what we have some images, and we want just to count how many people we have on these images. So we want these target labels, which are the real number of people on the image, which is, for example, here T1, T2, and T3. For each image, we suppose that we know the real number of people in this image. And we want to train a machine learning system. So the first step will be to have a feature extraction step. I don't go too much into the detail of the feature extraction. We will speak more about that later. But suppose that we are able to represent the whole image by a vector, x1, and each image has a representation as a feature vector. So what we want to do, we want to learn a function y, which could predict from the input feature here, x. We want to have something which is close to the target label. Okay, so this is a regression problem because we have an input x and we want to predict a value which is close to t. So this is the learning step, and of course we want not only to have this function, want not only this function to be accurate for predicting these labels on the training set, but we want it also to be able to predict for new images that have never been seen by the system. So this is the testing step, where in fact we will evaluate if the output of this function, this predicting function, which is here t hat, is close to t, and is it reliable, and is it able to generalize on new data? So if we consider this regression problem in 1D, it could be something that you may know, because this is a very simple problem where we have an x value, which is here one-dimensional, and we want to know this target value t, and we have some data points, which are the blue ones, and we have here an unknown function which is an ideal regression, an ideal solution. So in reality, we have only few data points, which are the blue points here, and we want to find this function y such that for each input point here, we have approximately the target value ti for every couple of value xt, which are our training data. So the training data is composed of some values in the training set associated to some labels, to some target values that we want to have. So if we take this very simple problem, you may know that we could do it by a regression, for example, with a polynomial. So if we take a polynomial of degree m, we could try to fit the coefficient of this polynomial in such a way we are close to the target values that we want. So if we want to solve this problem, what we will do, we will choose a loss function. The loss function, what is its purpose? The purpose of this loss function is to compare the output of the function for a given sample to the real output, so the ground truth output, what we want to have as value. And we compute an error, and we sum over all the samples. This loss has to be minimized. And in fact, we want to find the coefficient W0 to Wm such that this loss function is minimal. So here in this problem, we have several, we have an hyperparameter, which is m, which is the degree of the polynomial. For example, if we take degree 0, we will have just an horizontal line to determine only one parameter, which will be W0. If we have m equal 1, we have two parameters and so on. And we could see that if we increase the degree of the polynomial, in that case, we will be closer to the points, okay? But if we have, for example, in the training set, we have here 10 points. If we take a polynomial of degree 9, we will find a perfect polynomial which will pass through exactly all the points, okay? That's normal because we have as many points as the degree of the polynomial. So you could see here that this is perfect, but maybe this is not what we want, because in this case, we will not be able to generalize. So if we have new data, it will not work. For example, in this graph, we have reported the degree of the polynomial and the error after having fitted the coefficients. For example, here there is in blue the training set. So we see that while the degree is increasing, we have a better result. It means that the final error is low. And even if we are at the degree 9, the error is exactly 0. But the problem is that if we take other other data at test set, at test time, we could see that at the beginning it behaves right, but when we are at degree 9, the error will be very high. So this is what we expect by seeing this the preceding graph I've shown. So we want not only to find a function which is fitting well the training set, but we want this function to generalize well on new data. So this is a problem. So this is why every time we need two tests, two sets of data, what is called a training set, where we will try to minimize our loss, and a test set, where we will, a test set or a validation set, where we will monitor how the fitting behaves, and if we could generalize well or not on the data. So we will go again into this problem, and I will now focus on deep learning basics to understand what is deep learning and what are the functions we are considering to do our fitting in several cases, the case of regression and the case of prediction. So the basic unit that we have in deep learning is the neuron. And what is a neuron? in deep learning, not in the brain exactly, even if it is something which has been found to mimic the brain, but it's not exactly the same phenomenon. Here, a neuron is what? Is a unit where you have inputs, x1 and x2, several inputs, and one output. We have some parameters, which are here W1, W2, and B. B is known as a bias, and W1 and 2 are the coefficients. We have also a function sigma, which is called an activation function. And the output of the neuron is given by this equation. We are just having a polynomial, in fact, W1 multiplied by X1 plus W2 X2 plus B. And this value is transmitted to the activation function, which is basically a nonlinear function. We will go back to this function later. So the output of the neuron is a function f, which takes as input x values, the vector of inputs, which has some parameters, and the parameters are W, the set of W coefficient and the bias B. So this is equivalent to what we had before with the polynomial, where the coefficient of the polynomial were our parameters. Here, the parameters are these. And we could, of course, we could write this, this equation as a matrix equation or scalar product between W and X to simplify the notation. So basically, what can we do with a single neuron? If we, for example, choose an activation function which is a binary function with only +1 and -1 values, then and if I take W1 equal 1, W2 equal 2, and the bias equal -2, in fact, the output of the neuron will be simply the sign of this equation. So, for example, if we take these input points, I mean, this is x0, x1. I have reported in this graph x0, x1, x2, sorry, not x0, x1, but x1, x2. And the output of each value, for example, if I take 0, 0 as x1, x2, here we have the sign of 0 and the case, so it's not the right one, I think. 0, 0, 0, 0, yes, it would be. Okay, I think the no. So if I take 0, 0, it will be -2 here, and the sign of -2 is -1. So I reported this point in blue, because in blue are negative points, okay? If I take 0, 1, it will take only 2 times x2 -2, it will be 0. And the x1, x2, it is 0, 1, 0 on x1, x1, and 1 on x2, it will be this point, and so on. So we could see easily that the red points will be above this, this line, and the blue ones will be below the line, okay? So we have a decision boundary, whose equation is given by this formula. So basically, a single neuron in that case is doing just a simple separation between some positive sample and some negative samples. It is doing a kind of binary classification. If there is something that you want to know, don't hesitate to interrupt me. Okay, what can we do? In fact, a single neuron is very simple. We could use several ones, and if we stack several neurons, we obtain what is called a layer of neurons. And in a layer here, suppose that we have two neurons. We consider two inputs, and each neuron has its own output. So we have also two outputs. So doing the same calculation as before, we have for the first output, Y1, we have this formula with the weights associated to the red neurons here, which are denoted by first index 1. And for the green one, we have this equation with the weights associated to index 2. Okay, and we could suppose that this is the same activation function. So the whole equation could be also written as a matrix product. So we could express directly the output of the layer, in fact, which will be a vector of two values, x, y1 and y2, in function of the input vector x. So once we have seen this, we could also stack or put several layers. Suppose that we have here two layers, the first one here with two neurons, the second one with only one neuron. If we combine these two layers, it corresponds to a composition of two functions, okay? The first function, f theta 1 here will be the transfer function from the first layer, and f theta 2 will be the transfer function of the second one. And this is just a composition. So the global transfer function could be expressed again as a function of x and is given a single input output here, but it could be also several outputs. And the whole parameters of the system, theta here, corresponds to the whole matrix of all the neurons and also the bias of all the neurons. So what could we do with this kind of processing units, these neurons? We could think about processing an image. So how can we process an image with that? Suppose that we have an image as input. We want to use these neurons to take a decision. For example, we have an image, we want to decide if it is a motorbike, a bike, or a car. So how can we do? As we know here, we want to have single inputs for single or multiple input as input of our neurons. So we could do a first operation, which is called a flattening. We could say, okay, this image is a set of pixels. So what we could do, we could just make a very big vector composed of all the pixels of this image. It will be this big vector here. And this big vector will be the input of our layers. And it could be represented here as a set of neurons, which will be our input neurons in our system. So we could design several layers, and at each layer, we could decide the number of output we want. For example, here we have another layer, and then another layer. And what we will do, in fact, we will, starting from a very high number of layers, we will go progressively to a smaller number of layers to have, at the end, only 3 neurons, smaller number of neurons, not layer, smaller number of neurons, and to have, at the end, 3 neurons. Each of these 3 neurons will be will output a probability, which is the probability of being a motorbike, a bike, or a car. Okay. Here I have not represented all the connections because here each neuron is supposed to be connected to all the neurons of the preceding layer. So having these neurons and this architecture, we could think of having a prediction of the class of an image. But this is not, we have to introduce new other things to be able to understand how it would work. The first thing is, for example, if we look at the output, what do we want as output? We want to output some probabilities. So if we want to output some probabilities, we could use a specific activation function, which is called a softmax, whose purpose is to convert the values from the neurons, which are called logits, into probabilities between 0 and 1 to be able to have a probability, a prediction of some probability. So this function is basically to convert this logit into probabilities. For example, here, if you have these values for logits, 2, 1, 0.1, it could be also negative values. If you apply this function, you will see that we automatically have a high probability for the maximum value of the inputs here. This is why it is called a softmax. The softmax is converting the maximum value into a probability, which will have a high value, and the other values to some smaller values in such a way that the sum of these probabilities will be 1. So we have other kind of activation functions. A very famous one is the sigmoid, where we want to put a value between 0 and 1. There is another one which is very important in deep learning, which is the ReLU activation function. The ReLU activation function is a very simple idea. The idea is that we want to have 0 as output if the value is negative, and we want to keep the value as it is if it is positive. Okay. This activation function has a very good properties for convergence issues, so it is very much used. And we have also the softmax that I already presented before. So, in fact, what do we want? Recall that we want to solve a regression problem. So we have what? We have some training data with our X values and target values for a large number of data, n, let's say n couple of data. We have a loss function, which is able to compare the output of our function to the labels, to the target labels that we have. And we want this loss to be low, so we ça sert à quoi? C'est bon? Non. Alors attends, ouais. Est-ce que je dois reprendre?
Just maybe this technical trouble. You may have some questions.
Ouais, okay.
Is it clear? You have some questions before that? We'll continue.
Yeah.
It's okay.
Yes.
So in real neurons, so the neuron can target different target cells. And I see that you have one output, but this output can be connected as an input to different targets and the different layers, in the subsequent layers. So the inputs that the different target neurons, let's say, receive from one neuron, is it always is it always the same in your case, or can you design it so that a target neuron, say,
What do you-
receives slightly different?
What do you mean by
Uh,
target?
so-
Very
so,
different. The function could be different, yes. The
Right.
activation function from
Yeah.
one layer to the other
Yeah.
could be different.
Yeah, okay. I mean,
Okay,
just
if
to
it's
have a
that
broad
is
idea.
the
Okay,
question.
thank you, yes.
Okay.
Another question? I think we have to wait the WebEx
Okay.
is running again or not.
I don't know if I continue,
Okay, so maybe continue.
we could wait if there is something wrong on the WebEx side. Je vais essayer where. This is just a break.
Small break. Question?
Yes. Ah, this is a good question.
Yes, just to repeat, how to select the or to choose the activation function.
In fact, there is many parameters to choose. For example, the number of neurons, the number of layers, the activation functions. So this is what we call the deep learning engineering. So there are some previous work that have shown some implicit rules that we could choose to build our architecture. So it's not totally free. In fact, it's totally free, but we know that some configuration will not work well. So there are some, let's say, rules,
Receipt.
that we must use to have good systems, because otherwise it will not converge, or it will not generalize well, it will not go very well. So I will try to give you some information about that during this course, because we will go into the details, more and more into the details, and try to build some small architectures. And you will also do other architecture in the practical sessions. But most of the time in a deep learning system, we use the review activation for the first layers. And after the last layers, we have to do differently. For example, the softmax, if we want to do a probability estimation. So this is a global rule, but there can be some exception and some other sources.
Okay. I think we can continue. Perfect.
Okay.
Thank you, Christophe.
So basically, we want, as I said, we want to find the parameters of our neurons. So let's say we have chosen the architecture. So the number of neurons, all the architecture is fixed. Either the number of weights. So it means that the number of weights, the number of inputs, all the activation functions are known. So this function f is totally known, except the parameters that we have in each neuron. So the goal will be to try to find the parameters. So this is the same process as we had before with our polynomial regression, that we want to minimize the loss. We want to find the parameters, the set of parameters theta, in such a way that we minimize the loss L. So here, if we represent the loss function in 1D, of course, you could imagine that it is a very high dimensional function here, because the number of parameters, the global number of parameters is very high. It could be several millions of parameters. And we want to find the parameters. So the training will be the process of finding the parameters, and how it can work. In fact, we are just doing a kind of gradient descent. This is globally the idea of all the deep learning architecture. So we start from initial state, initial set of weights for all the neurons. And we try to modify slightly the weights in such a way we go towards the minimum of the function. Okay, so we have in this process we have to compute a gradient over all the parameters, and we want to modify the parameters in the direction of the gradient to be able to minimize the function, so to modify slightly the parameters to minimize the function. So there are a lot of algorithms to do that. And basically, if we want to minimize this function using the definition I gave here, in this definition here, I sum over all the sampling points, so the training points. So I mean, if I have, for example, 1 million images as training, each image has a lot of pixels. So it means that this sum here will be very, very high. So in practice, it is impossible to compute this function at each step of the gradient descent. So what do we do? In fact, we are using a modified algorithm, which is stochastic gradient descent. The stochastic gradient descent is the other algorithm, which is very simple. Okay, instead of taking all the training sample to minimize the loss, so to compute the gradient, we will only choose one sample. Okay, we take randomly one training point, and we compute the loss for this training point. We compute the gradient for this training point, and we modify all the weights of the neurons according to this sample. This is the stochastic gradient descent. And after, we take another sample randomly, and we do it. So at each gradient step, in fact, we choose one sample. So this is the other extremity of this algorithm. The first is to use all the samples. Here is to use one. In fact, what is more efficient is to be in between, which is called the mini batch gradient descent. What is done in the mini batch gradient descent? We are not taking only one training sample, but we are training a small set of training sample. Okay, so in fact, we are taking all the training samples. We are splitting these samples into small sets. Okay, and we are doing that randomly. And at each iteration of the gradient descent, we are taking one different small set of training sample, which is called a mini batch. Okay, at each step, we take a mini batch, and at the end, when we have seen all the training set, it means that we have considered all the possible mini batches. Then we have done what is called an epoch on the algorithm. Okay, so this vocabulary is important to know. I will not go into the details of the algorithm. It is not the purpose here, but just understand the principle of this algorithm, that at each step we want to modify the parameters, and to modify the parameters we take only a subset of training sample. So we have to consider several iterations to see all the training set. And when we have seen all the training set, we have passed one epoch of training. Okay? I will not go too much more into the detail of this algorithm. I will now focus on loss functions. So I said that it is important to choose activation function, of course, but the most important part of the system, of the deep learning system, is the loss function. Oh, sorry. Is the loss function. So the loss function is the way we compare the real output of the system to the target that we want. So this loss function must be chosen in agreement with the task that we want to solve. And for example, if we have a classification task, the classification task, we have, for example, here 3 tasks. Suppose that we want to know if, in an image if the weather is cloudy, if the weather is nice, or if it is the night, for example. So we suppose that for that, we will have 3 outputs in our system, which ideally should be binary values. If it is cloudy, I want this value to be 1 and the other one to be 0. If it is sunny, I want the first one to be 1. And if it is the night, I want the second one to be 1. Okay? This is our target. And in fact, in our system, I will have the output of our neurons, which will be the Y values. And we want to compare the Y values to these targets. So we are comparing in using a distance between densities, in fact. And for that, we use a function which is called a categorical cross entropy, which is defined by this equation. And the value Y are our probabilities, which are the output of our softmax function. Okay, so we have 2 important losses to know in this introduction: this cross entropy loss and the mean square error I already introduced for the regression. These are the main losses that we could use in this kind of system. Here I will not go too much into the details. So practically, how will it work? We will use a framework, a Python framework, which will do most of the calculation for us. So, for example, in the tutorial this afternoon, we will use a Keras framework, which is based on TensorFlow. And you will see here, I will just detail that it is very easy to understand, even if you don't know much about the details of the deep learning or the framework. Here we have, for example, a data loader, which is loading some data. So we are loading our 2 vectors, X corresponding to the input and Y corresponding to the output. Here it's our T values. This is the target values that we want. These are the labels associated to the data set. Then here we just do some conversions for the labels. For example, in the training and the test set, it's not very important. Here is the definition of the network. So we want to do a network with a first step, which is a flattening. Remember that what I showed here, the flattening is the process of converting a square image into a vector, okay? And then in our system that I will comment here, we will only have one layer. So it means that we start, or no, 2 layers. We start from the input, which is the set of input neurons, and we will directly go into the probabilities. Okay, there will not be any other layers. So this is what is it here? There is the flattening. So this is the input layer, and then there is what is called a dense layer, which will be the output layer with only 10 neurons. Okay, and we set the activation function as a softmax because we want here to have 10 values as probability. The data set used here is a data set composed of some digits. So we want to predict if the digits are 0, 1, 2, 3, or until. Okay, we have a model, we design a model, and in the model we choose a loss, which is here a categorical cross entropy, an optimizer, and this optimizer will be a stochastic gradient descent with a learning rate, which is fixed here to 1, and we will have a matrix in the end to measure the accuracy of our classifier, which will be here accuracy metrics. So I forgot to point out that the most important parameter here, or maybe I will tell it after. One of the most important parameter in this algorithm, this gradient descent algorithm, is what is called the learning rate, this eta. It is how much we modify the parameters at each step, okay? So this is a very important parameter, and we have to be careful to choose this parameter, otherwise it will not converge at all. So here are these instruction. There is the fitting part where here all the training is included in this function call, okay? This function fit will train the model over 10 epochs with a batch size given here. What is the batch size? The batch size is the number of samples or training samples that we are taking for, remember, our mini batches. I say I split my data set into mini batches, into small groups. Here I said that the small group will be this size and there will be 10 epochs, okay? And then after I could have the final score of my model by this function evaluates. So you will have the occasion to go more into the details during the tutorial where you will just train first a classification model on some medical images that will be given in the tutorial. So the learning rate is the most important hyperparameter because it controls the step of the gradient descent. And how are we able to fix it? In fact, we are doing some trials. And for example, here, consider that we have plotted some curves, giving here in x-axis the epoch, the number of epoch, and in the other axis, the value of the loss. So what is very important is when you monitor this curve, that you have a decreasing curve. We must have a sharp decrease and then a decrease which will be less sharp. If you have something which is decreasing and then increasing, it means that you have a too high learning rate. Maybe you have too high learning rate. If you have a high learning rate, not too high, giving a kind of exploding loss, you may have very fast saturation of the result if your learning rate is too high. So a common strategy is to change slightly the learning rate during the training to be able to avoid this kind of saturation of the learning rate. And the right curve could be something like that, where you have this kind of learning. It's not very easy to determine, but there are some strategy. I will not go too much into the details. There are some optimization algorithms that could give you the right learning rate. There is something else we have also discussed a bit. What was the problem of the overfitting? Here, this is another curve. This is not the loss curve, this is the accuracy. The accuracy curves are on the other side because we want the accuracy to be high. The accuracy is for example, the number of samples or the ratio of the correct classified samples. Okay, so ideally it should be 1, the accuracy, the maximum accuracy. So if you monitor the accuracy, you could monitor the loss, but you could also monitor the accuracy. If you monitor the accuracy, you should have an increasing curve. And if you monitor both the training accuracy and the validation accuracy, you have to be careful about how these curves are evolving. And if you have something like that, for example, the validation is going down, whereas the training is still going up, it means that you have a kind of overfitting phenomenon. So it means that you may have too much parameters. Remember our polynomial, too much parameters on not data, not much data. So if you don't have high number of data and you have too much parameters, you will have this kind of phenomenon. And one way to overcome this will be to stop the learning when you see this kind of behavior. So there are some specific functions in Keras to automatically stop the learning, which is, for example, what is called early stopping, to avoid to go too much into this region, because what it means is that the model is learning by heart all the training samples. Remember the polynomial, we are going exactly to the value of the training samples. And if we have new data, it will be very bad. This is why these curves are diverging. So one way to avoid or to limit this kind of overfitting is to do what is called data augmentation. What is data augmentation? When you have images, you make some changes, geometrical changes or color changes into your images. In such a way, you increase the diversity of your images. So it is like you had more images, but in fact, you are artificially making some new images. So this strategy, most of the time, improves the training. Okay. So I'm going very fast, but in fact, we will practice this afternoon. So now we have seen a very simple neural network, which is what we call the fully connected neural network, fully connected because we have for each neuron all the possible connection to the next one. So in image processing, this is not the ideal situation. And in fact, when we process images, we prefer to have what is called local connectivity around the neuron and also parameter sharing. So I try to make an image of that. In fact, instead of having a neuron connected to every pixel of the image, I mean, if we connect to every pixel, it means that the output here will depend on the whole image, okay? And the output of this one will also depend on the whole image, and so on. Here, I don't want that. I want this neuron to be the result of some local operation on some small patch of the image. Okay, so in this situation, I will only connect my neuron to some small set of pixels, which are all near the same region. And I want the output to be a value, which is a kind of integration of the information around this region. Okay, and it will be the same for each neuron here. I take another one, and I want this neuron also to integrate information about this region. And I will also put another constraint, which is the translation invariance. Because in fact, when I look over an image, look at an image, I don't want to do specific processing on each region of the image. I don't want to do some processing here and some other processing here, some other processing here, and so on. Because all the regions must be treated the same way, in fact. So I want not only my neurons to integrate local information, but I want also my neurons to share the same weights. So it means that the operation I will do on each neuron will be the same, whatever the region. Okay, this is what I call the translation invariance, and which is which is here denoted by parameter sharing. All these neurons of this layer will share the same parameters. So if you are a bit familiar to image processing, you will know that this kind of operation is a convolution operation. So are you familiar? Some of you are familiar to convolution operation? The convolution operation is exactly what I presented before. This is just here an example. Convolution operation, I take my image. I have what is called a filter, which will be a set of weights that I want to use to do an operation, a specific operation. I apply these weights on my region, and I do a kind of sum of products between my input and my filter. In such a way, I obtain as an output a single value. So here, this is 4 times 1, 9. So 4 times 1, 9 times 0, plus 2 times -1, plus, and so on. So I do this operation for all the region to have a single output value. Okay? So in this process, I take my filter here, and I move my filter step by step over all the image to have a matrix as output, which will be another image. Okay? The output image will have less pixels because suppose that here we have 6 input pixels. The filter is 3. So if I want to move my filter in such a way I don't go out of my image, I could go into this 9. 4. I will have 4 values as output only. So this image will be basically smaller. But it could also be the same size if I use some padding. If I add some zeros around, I could have the same number of pixels. Here, the padding will control how many zeros I add around. Here, the padding is 0. And we also have the stride. What is the stride? The stride is how much I move my filter to the next position. Okay, I can move only 1 pixel. This is stride equal 1. This is the most frequent situation. And the size of the filter, which is 3. Okay, so if I come back to my image here, when I apply a convolution filter, I obtain another image. Here, if it is like a gradient, like this filter is like a vertical gradient, I have something like that where I could see the edges of my image. So this convolution operation, I could do it several times. Okay, I could take another filter with different values and compute another image. Okay, these two images are called feature maps. Okay, because they are in fact images or some information extracted at each pixel from the source image. And we could do this several times. Here I use 4 filters to have as output 4 feature maps. Okay, so my neural or my in fact my layer here will not consist of a huge number of neurons as before. It will consist of some set of filters. Here I have 4 filters, and each filter is 3 by 3. Most of the time in deep learning, we are using 3 by 3 filters because they are more easy to compute. And if we do successive filtering operations, it will be equivalent to have bigger filters. So here, the number of parameters we have only 9 parameters per filter, plus 1 bias. I didn't mention it, but there is all the time a bias. So just a constant value that we will add after the convolution. It will be the bias, and the bias could be different from one filter to the other one. Okay, so the total number of parameters here will be 9 times 4, plus 4 with the bias. Okay, so it will be much less than if we had taken a fully connected layer. So we have our 4 filters 3 by 3, and then we have 4 feature maps. And these feature maps, in fact, it could be considered as a single feature map with 4 channels. So it is the same as saying we have 4 feature maps, or we have a feature map with 4 channels. Let's consider that it is like if you had a multispectral image, for example, that you have a lot of similar images which corresponds to the whole information that you want to keep. These are the channels. And if we want to do something else, in fact, we will want to add another layer. And if we want to add another layer, we want to do again some convolutions, but as input, we will not have only one image. Here, we will consider at the beginning, it could be, of course, it could be 3 channels here if it is a color image, but I've considered till now that it is only a single channel image, okay? Let's consider that the first convolution was for a single channel image, but here we have 4 channel image, and we want to apply a convolution to this 4 channel image. So it means that each filter will not only be a 3 by 3 filter, but it will be a 3 by 3 times 4 filter. I mean, it is like we have a volumic filter that we will apply over all the channels, okay? So this is just detailed here. I have maybe to be careful not to be, because the time is running. Okay, so here, this is a multi-channel convolution. We have 3 input channels. For each channel, we have a different set of filtering parameters. Okay? And the whole convolution will be a combination of the 3 convolutions here, and we will just sum the results. It is like if we add a volumic filter here, and that we are computing. For each output, we are integrating all the information over the channels. So basically what we will have here, another feature map will be a combination of these with a filter, and we could also have another filter. That's why I put 2 filters here. So at the end, there is another type of operation that we have to do also. This is what is called pooling operation. What is a pooling operation? It's much more simple. The purpose of a pooling operation is to change the number of pixels that we have. So this is a specific filter, for example, here called max pooling, where we take every 4 values here and we take the max, and we only keep one out of these 4 values, here the 7, and so on. So this will decrease the resolution of the image. So these are, for example, the 2 first layers, which are convolutional layers. Then here, a pooling layer. So at the output of this pooling layer, I will have some smaller image. So then, if I go back to a normal or a full convolutional layer, all this convolutional network will have this kind of architecture where we have as input an image. We have several convolutional layers associated with some pooling layers. Here, we have merged the 2 information, convolution plus pooling. So it means that from this feature map, we are doing convolution plus pooling. So what do we have? Here we have 3 channels as input. And then as output, we have more than 3 channels. And most of the time, we increase the number of channels and we decrease the spatial resolution, the spatial definition. So there will be a set of layers here to go to a smaller spatial support and a higher channel dimension. It means that we will have here a high number of channels, typically 200 or 1,000 of channels here. And what is beyond that? Beyond that is that when we increase the number of channels, we are here describing the semantic content of the image. So it means that at each point of this feature map, we have an information which could be a feature vector. And this feature vector is telling us information about the visual content of the image. So is it, for example, a kind of head of an animal? Is it some ear? Is it an eye? Is it something else? Okay, the much we are going inside the network, the more we are going into semantic information. Then this first part is what is called the feature extraction part of the network. Then we have the multi-layer perceptron that we already discussed about by taking a flattening layer and then using normal neurons that we discussed about already and going to the last layer when, for example, here we will output some probabilities of being horse, being zebra, or being dog. Okay, is it clear till now? We see some basic operations that we have to do if we have an imaging system or a computer vision system where we want to input an image and we want to output some probabilities predicting the class of these images. And this structure is general. So I will not go too much into the details. Here are just some instruction to add some convolutional layers. Okay, here I add a 2D convolutional layer which will be of size 3 by 3 with 74 filters. Okay, I take 74 filters. So it will output 74 channels or 74 feature maps. And I choose an activation which is a ReLU. Here is the input size of the image. It's not mandatory to specify it. There will be another one. There will be a max pooling. There will be a flatten. There will be a dense layer and another dense layer. Okay. All these instructions are describing the architecture of the network. Yes. Yes.
Your maps and you can estimate features. On flatten layer, is it a combination of all the last feature maps or
no?
No.
The flatten layer is all the information from all the channels. Okay.
Sorry.
So this is all information from all the channels. I take this pixel, this pixel, this pixel, this pixel, this pixel, and this one, this one, this one. The number of dimension we have here, it is this one times this one times this one. Okay?
Was there a question?
Okay, so this is in fact, as we process, we will process all the information from all the feature maps. Okay? But we will not anymore consider some local information. We will integrate all this information. This is important to understand what is the process being that. Here in the first part, we want to extract some features. So we want to represent each pixel by a feature vector. Okay. And then here we have all the feature vectors. And we want with all these feature vectors, we want to take a decision. And we take it gradually by adding some fully connected layers, which will process, which will mix all the information from all the pixels and all the channels, okay? And doing this, in fact, it will also be like if we compute this separator between the points, in fact. We have the feature vector, which could be seen as some points in some high-dimensional space. And here, in this part, we are changing a bit the space. We are adapting the space. And at the same time, we are computing a decision function to separate the points of different classes. Okay? This is basically what we are doing at that part. And I said before that in a classical machine learning system, we have first the feature extraction and then the classification. Here we have all these steps mixed. So it means that the system is learning not only the classification part, which is here, but it is also learning the feature extraction part. This is why we need a lot of information for that. And for example, here is a classical architecture, which is called VGG60. So it is important to know what is the architecture of some classical systems. Here in this VGG16, you have 16 layers, in fact. You could see in the legend here that we have convolutional layers plus ReLU activation are denoted in black. Max pooling are denoted in red, fully connected are denoted in blue, and softmax, it is a kind of yellow or brown that we have. Okay? So as input, we have here an image which is 24 by 224 times 3, because this is a color image. Okay, so there are 3 channels. Then you have a first convolution plus ReLU, which is here. Then another one, convolution plus ReLU. These convolution plus ReLU have 64 channels as output. Okay, so this is first we have 3 channels, then we have 64. So from here to here, there is one filtering operation with 64 filters, which are 3-dimensional filters. Then from this one to this one, we have another 64 filters, but these 64 filters are volumic filters of size 3 by 3 by 64. Okay? So this is 2 times. Then after you have a max pooling, so the definition is divided by 2. Then you have another time filtering, and you have set this time 128 filters, then 128 filters, another pooling operation, so the resolution is decreased again, and so on. Here at the end, you have 7 by 7 image. In fact, this is a very small image at the end with 512 channels here. So this is a very high number of channels. Then you have the fully connected layers. You have a fully connected layer with 4,000 neurons here, another one with 4,000 neurons, and then after the last one, which is one with 1,000 neurons. Why the last one is 1,000 neurons? Because this system is doing a 1,000 classification task, because it is classifying a data set which is called ImageNet, which has 1,000 classes, different classes. And this is at the end a softmax to predict some probabilities. Okay? So there are a lot of weights, and the total weights, number of weights that we have to learn in this system is this number. So this is 100 million of weights to learn in this system. Okay, so as the time is running, I will not go much into the details for the last things. The notion of receptive field is interesting also. When you consider some convolution operations, even if you have only 3 by 3 operations, if you chain several convolution operations, it is like if you were analyzing a higher region of your image. Here, it is easy to understand that this neuron is function of a bigger zone in this feature map. So there is a formula here. So each time you are going inside your architecture here, each pixel in this feature map corresponds to a larger zone of the image. So I also speak about ImageNet. ImageNet, what is it? It is a big data set, big image data set, which has been built over WordNet hierarchy. WordNet is a hierarchy of words. It is a lexical database to organize the words into meanings, into groups. And it is widely used in deep learning. There is a subset of this WordNet, ImageNet, which has been used for a challenge. And this dataset has 1,000 categories. There are 1.2 million of images for training. This number of images for validation and test. And to store it, you need 300 gigabytes. So it's very big. And so it's not so easy to learn or to train a system using this data set, but hopefully a lot of deep learning systems have already been trained on this data set, and we could use them directly, use the weights of the trained architecture in our problems without needing to retrain them. So I just want to speak a bit about what is called transfer learning, because in fact, as Carol said, in medical images problem, and even in most practical imaging problems, we don't have access to a lot of annotated images. So this is a big problem. So if we have very few images, it will not be able to train the whole architecture because we don't have enough images to train. We will have overfitting. It will not work. So how can we do with that? How can we solve this issue? We are doing what is called transfer learning. What is the idea behind that? The idea is to use a model which has already been trained on a large data set, let's say ImageNet, and we want to use it to leverage the training that we have to solve another problem. So how can we do it? The idea is here, the network has been drawn here in simplified drawing. So we have the convolution part here, and we have here the fully connected part. So the idea is to keep some part of the existing network and add new neurons at the end, for example. So if we have very few images to train, we will keep all the first layers that have been previously trained. We will add new neurons at the end, or we could also discard the last convolutional layer and replace it by another one. And we will only train the new neurons that we have added. So first, we have previously trained model. We remove the last layer of the model, those which was inferring the probabilities. We add a new layer adapted to our problem. We freeze the weights of the first layers, so it could be all the layers which are in the convolutional parts and some on the fully connected parts, and we train only on the last layers. Okay, so it will be a way to train with few number small number of data. So there are several options that you could do. You could either freeze all the layers and try only the last one, or you could also unfreeze some layers. And here I put some strategy that you could use. For example, depending if your data is a large amount or small amount, if your data is similar or dissimilar to ImageNet, and if different, what is different? Different from 5 freeze cross layer. And these are
different from ImageNet.
Yes, it could be different from ImageNet, but I guess this one was also different from ImageNet. So if you have a large amount of data and your yes, it depends if the classes are different of or similar. I don't remember. So either you fine-tune all the layers. Yes, no, similar is different. Yes, it's similar or different. Yes, it's from the class. If the classes are very different, you must retrain from scratch. If they are similar, you could fine-tune all the layers. If you have very small amount of data, you could freeze all the convolutional layers. If you have similar data than ImageNet, and if you have different data, you could freeze only the first convolution layers. It's not that exactly, but okay, the idea is there. Okay, so I don't know if I go to the semantic segmentation or if I stop here. Maybe it will be enough for you. That yes, I could. Okay, so I go just a little further. If you are still ready to continue, is it okay till now? Okay. So in fact, till now we have considered a simple problem where we want to infer a single value, which is a class. But in some problems, as Carol said, we want to predict one value per pixel. For example, in what is called semantic segmentation, suppose that you want to understand what is in the road. You want to know where are the car, where is the road, where are the pedestrian or the people. So you want as output to have an image where each pixel is telling you what kind of object or what kind of class you have. Okay. So this is different from what we did before, because before we had only one value as output. So a standard CNN, a standard convolutional network for classification, has some convolutional layers, as I said, with pooling, which reduce the spatial dimension and increase the channel dimension. Then we have full connected layers, and we have a single class prediction. So we lose the spatial information that was initially in the image. So we need an architecture that could produce a spatially dense output. So an architecture that could reconstruct a map predicting classes. So the general idea is to consider that we have the first part of the architecture, which is what we saw till now, which is what we will call an encoder. The encoder will basically decompose the image and by reducing the spatial dimension and augmenting the number of channels. So we will add another part of the network, which will be called a decoder. So the purpose of the decoder will be to increase again the definition of images and to predict a class, a pair pixel class. In such kind of architecture, this part will be called a bottleneck. This is like a bottle that you reduce the spatial support, and then after you will increase it again. And the part where you increase will be called a decoder, where you will progressively upsample the image to recover this spatial information. So how can we do that? We could do that by some tool which is called transpose convolution or up convolution. So if we go back to some convolution, normal convolution, here this is a direct convolution. Remember that we put a filter and we move this filter across the image to have a value for each position of the filter. So we want to do something which will be the inverse. So how can we do that? We take our initial pixels here, which are blue. We add some zero values in between each pixel. In such a way, we increase the spatial resolution by adding some zeros. It's a strange strategy, but it could be done like that. And then we are applying again a filter here, which will integrate the information of here the blue pixel, and it will take also the zero value, which will not give much information, and we will have as output a value. And as we have increased the resolution, we will have as output more values than as input. Okay, this is basically how works an up convolution. And the same way that we were learning our filters in the encoder for normal convolutions, we will also learn the values that could reconstruct or that would recover the definition of the image. It's a kind of interpolation, in fact, that we are doing. Okay, this is a kind of interpolation between the pixel that we have, and with this interpolation, we are doing, and we are integrating the information. So we insert some zero, and we applied a learned convolution term. We could do this with border, it's not important. So there is another trick that we have to do. It is what is called the problem of skip connections. If we do what I told you here, I mean, starting from very low resolution and making the resolution increase from here to here, we will face some problem. And the problem is that we will have a kind of pixelization, because in fact, we don't have details anymore. Because if we start for very low resolution and we want to recover high resolution, it will be very difficult. So the trick is to use what is called some skip connections. And skip connections are some shortcuts between the encoder and the decoder. So I will go just until UNet. So the classical architecture that we use, Carol already talked about this. It is an architecture called UNet, where you have here the encoder which is decreasing the resolution and augmenting the number of channels. Here is the decoder, where you have up convolutions, and in between you have those skip connections, which are directly transferring information from the encoder to the decoder at equivalent resolution. Okay, and in fact, with UNet, we are concatenating information. We are taking this information here, and we are concatenating them close to the information which have been up convolved here. So we are, in fact, at each step, we are taking those feature maps here. We are doing transpose convolution to recover bigger feature maps, and we are concatenating the feature map from the equivalent resolution from the encoder just here at that step. And concatenating means that we are putting as new channels, okay? We are putting this information as new channels in such a way that when we are going at the next step, we will integrate all this information by the filter that will be used as multi-channel filter, which will be a NUG convolution filter here, which will process all the channels and will integrate not only information from the lower levels here, but also spatial information that have been directly transmitted from the encoder. Okay. What to say more? I think this is basically what you need to know to understand. There is here the detailed architecture, but I will not have much time to go into the details. So I think this is enough for me. I just I've written down the take-home messages. So I put them on the screen, and if you have questions.
Thank you, Christophe, for this talk.
Okay.
Have you some questions?